Let's get a little bit more deep into how Spark works. We're going to talk about the Resilient Distributed Data Store, known as RDDs. It's sort of the core that you use when programming in Spark. And we'll have a few code snippets to try to make it real. So let's have a look. So we're going to give you sort of a crash course in Apache Spark here. There's a lot more depth than what we're going to cover in these next few lectures, but I'm just going to give you the basics you need to actually understand what's going on in these examples and hopefully get you started and pointed in the right direction. So the most fundamental piece of Spark is called the Resilient Distributed Dataset, an RDD. And this is going to be the object that you use to actually load and transform and get the answers you want out of the data that you're trying to process. So very important thing to understand. It stands for Resilient Distributed Dataset. So it is a dataset at the end of the day. It's just a bunch of rows of information that can contain pretty much anything. But the key is the R in the first D. So it is resilient in that Spark makes sure that if you're running this on a cluster and one of those clusters goes down, it can automatically recover from that and retry. Now, that resilience only goes so far, mind you. If you don't have enough resources available to the job that you're trying to run, it will still fail, and you will have to add more resources to it. And there's only so many things it can recover from. I mean, there is a limit to how many times it will retry a given task. But it does make its best effort to make sure that in the face of an unstable cluster or an unstable network, it will still continue to try its best to run through to completion. And obviously it is distributed. The whole point of using Spark is that you can use it for big data problems where you can actually distribute the processing across the entire CPU and memory power of a cluster of computers. And that can be distributed horizontally, so you can throw as many computers as you want to a given problem. The larger the problem, the more computers. There's really no upper bound to what you can do there. Now, you always start your Spark scripts by getting a Spark context object, and this is the object that sort of embodies the guts of Spark. It is what is going to give you your RDDs to process on, so it is what generates the objects that you use in your processing. You don't actually think about the Spark context very much when you're actually writing Spark programs, but it is sort of the substrate that is running them for you under the hood. If you're running in the Spark shell interactively, it has an SC object already available for you that you can use to create RDDs and whatnot. But in a standalone script, you will have to create that Spark context explicitly, and you'll have to pay attention to the parameters that you use because you can actually tell the Spark context how you want that to be distributed. Should I take advantage of every core that I have available to me? Should I be running on a cluster or just standalone on my local computer? So that's where you set up sort of the fundamental settings of how Spark will operate. So let's look at some little code snippets of actually creating RDDs, and I think it'll make a little bit more sense. So here's a very simple example. If I just want to make an RDD out of a plain old Python list, I can call the parallelize function in Spark, and that will convert a list of stuff, in this case just numbers, 1, 2, 3, 4, into an RDD object called nums. So that is the simplest case of creating an RDD, just from a hard-coded list of stuff. And that list could come from anywhere. It doesn't have to be hard-coded either. But, that kind of defeats the purpose of big data, right? I mean, if I have to load the entire data set into memory before I can create an RDD from it, what's the point? So I can also load an RDD from a text file, and that could be anywhere. So in this example, maybe I have some giant text file that's, the entire encyclopedia or something. And I'm reading that from my local disk in this example. But that will actually convert every line of that text file into its own row in an RDD. So you can think of the RDD as a database of rows. And in that example, it will load up my text file into an RDD where every row contains one line of text. And I can then do further processing in that RDD to parse or break out the delimiters in that data. But that's where I start from. Remember when we talked about ETL and ELT? So this is a good example of where you might actually be loading raw data into a system and doing the transform on the system itself that you use to query your data. So you can take raw text files that haven't been processed at all and use the power of Spark to actually transform those into more structured data. It can also talk to things like Hive. So if you have an existing Hive database set up at your company, you can create a Hive context that's based on your Spark context. And how cool is this? You can actually create an RDD, in this case called rows, that's generated by actually executing a SQL query on your Hive database. So that's an example of also creating an RDD. And there are more ways to create RDDs as well. You can create them from JDBC connections. So basically any database that supports JDBC can also talk to Spark and have RDDs created from it. Cassandra, HBase, Elasticsearch, also files in JSON format, CSV format, sequence files, object files, and a bunch of other compressed files like ORC or what have you. I don't want to get into the details of all of those. You can, go get a book and look those up if you need to. But the point is, it's very easy to create an RDD from data wherever it might be, whether it's on a local file system or a distributed data store. Just to call attention to that again, up here I'm loading from a local file using the file URL system, but I could also use S3N if I wanted to host this file on a distributed Amazon S3 bucket, or HDFS if I want to refer to data that's stored on a distributed HDFS cluster. And that stands for Hadoop Distributed File System if you're not familiar with HDFS. When you're dealing with big data and you're working with a Hadoop cluster, usually that's where your data will live. So again, RDD, just a way of loading and maintaining very large amounts of data and keeping track of it all at once. But conceptually, within your script, an RDD is just an object that contains a bunch of data, and you don't have to think about the scale, because Spark does that for you. Now there are two different types of classes of things you can do on RDDs once you have them. You can do transforms and you can do actions. So let's talk about transformations first. So transformations are exactly what it sounds like. It's a way of taking an RDD and transforming every row in that RDD to some new value based on some function you provide. So map and flat map are the ones you'll see the most often. Both of these will take any function that you can dream up that will take as input a row of an RDD, and it will output a transformed row. So for example, you might take raw input from some CSV file, and your map operation might take that input and break it up into individual fields based on the comma delimiter, and return back a Python list, for example, that has that data in a more structured format that you can perform further processing on. And you can chain map operations together, so the output of one map might end up creating a new RDD that you then do another transformation on, and so on and so forth. And again, the key is Spark can distribute those transformations across a cluster. So it might take part of your RDD and transform it on one machine, and another part of your RDD and transform it on another. Now, like I said, map and flat map are the most common transformations you'll see. The only difference is that they differ in that map will only allow you to output one value for every row, whereas flat map will let you actually output multiple new rows for a given row. So you can actually create a larger RDD or a smaller RDD than you started with using flat map. Also, filter can be used if what you want to do is just create a Boolean function that says, should this row be preserved or not, yes or no. And there are some less commonly used transformations as well, like distinct, which will only return back distinct values within your RDD. Sample lets you take a random sample from it, and then you can perform intersection operations like union and intersection subtract, or even produce every Cartesian combination that exists within an RDD. Here's a little example of how it might work. So let's say I created an RDD just from the list 1, 2, 3, 4. I can call then rdd.map with a lambda function of x that takes in each row, each value of that RDD, calls it x, and then it applies the function x times x to square it. So the output of this, if I were to then collect the output of this RDD, would be 1, 4, 9, and 6, because it would take each individual entry of that RDD and square it and put that into a new RDD. Okay, makes sense? Now, if you don't remember what lambda functions are, we did talk about it a little bit earlier in this course, but as a refresher, the lambda function is just a shorthand for defining a function in line. So lambda x colon x times x is exactly the same thing as defining a separate function that we named called square it, that returns x times x, and saying rdd.map square it. So it's just a shorthand for very simple functions that you want to pass in as a transformation. It eliminates the need to actually declare this as a separate named function of its own. And that's the whole function of that's the whole idea of functional programming. So you can say you understand functional programming now, by the way, but really it's just shorthand notation for defining a function in line as part of the parameters to a map function, or any transformation for that matter. You can also perform actions on RDD. So when you want to actually get a result, you can call collect on an RDD, and that will give you back a plain old Python object that you can then iterate through and print out the results or save them to a file or whatever you want to do. You can also call count, which will force it to actually go count how many entries are in the RDD at this point. Count by value will give you a breakdown of how many times each unique value within that RDD occurs. And you can also sample from the RDD using take, which will take, some random number of entries from the RDD, or top, which will give you the first few entries in that RDD if you just want to get a little peek into what's in there for debugging purposes. The more powerful action is reduce, and that will actually let you combine values together for a same common key value. So you can also use RDDs in the context of key value data. And the reduce function lets you define a way of combining together all of the values for a given key. So very much similar in spirit to MapReduce. So using reduce is, basically the analogous operation to a reducer in MapReduce, and map is analogous to mapper. So it's often very straightforward to actually take a MapReduce job and convert it to Spark by using these functions. Remember too that nothing actually happens in Spark until you call an action. So once you call one of those action methods, that's when Spark goes out and does its magic with directed acyclic graphs and actually computes the optimal way to get the answer you want. But remember, nothing really occurs until that action happens. So that can sometimes trip you up when you're writing Spark scripts, because you might have a little print statement in there and you might expect to get an answer there, but it doesn't actually appear until the action is actually performed. So let's go into let's talk a little bit more about MLlib next and get into more details about how this works conceptually. So that is Spark 101 in a nutshell. Those are the basics you need for Spark programming. Basically, what is an RDD and what are the things you can do to an RDD? And once you get those concepts, then you can write some Spark code. Up next, we'll talk about MLlib and some specific features in Spark that let you do machine learning algorithms using Spark.